Добрый день. Меня зовут Кирилл Зиборов.
Hello, I'm Kirill Ziborov. I'm an engineer responsible for formal verification at Positive Technologies.
формальными методами.
For the past 5 years, I've been involved in these formal methods, trying to apply them to secure blockchains at different levels. So the plan today is, or rather tonight, is to discuss formal verification of BFT consensus. First thing first.
Поговорим вообще, дадим определение того, что такое консенсус, да, то есть это
Let's define consensus. A consensus algorithm is an algo that helps nodes in the distributed system arrive at a shared value.
Возможно, ненадежности сети.
Given that the network at times cannot be fully trusted, we'll talk about this degrees of trustlessness.
Под значением обычно понимается хэш.
When I say value, I mean the hash of the next block in a chain.
Соответственно, какие бывают же ненадежности?
So,
ненадежности можем разделить на.
What can happen? In fact, I want to provide two buckets here. In fact, we can be talking about consensus algos of two types, depending on how tolerant they are. One is crash fault tolerance. Here, the assumption is that nodes cannot be malicious, but they can go down. They go down, and sometimes they will spring back into action, sometimes they won't. And therefore, because some nodes go down, some messages can be lost. There could be other failures in the chain. We will not be talking about this type. We'll be talking about BFT. So in BFT, the assumption is that nodes can be malicious. So if a node is a leader, it can, for example, reject specific blocks, do some censoring, or only accept the blocks they find most profitable to accept. Moreover, they can send erroneous or conflicting information if they want the blockchain, for example, to stop.
И определим уже конкретно BFT алгоритм консенсуса.
Now, let's provide a definition for BFT in a purely mathematical way because we want to do it formally. I mean, we want to verify it formally, and that requires mathematical tools.
Пусть у нас есть n узлов в распределенной системе.
So let's assume we've got n nodes in a distributed system, and some of them are Byzantine, and we'll be calling them F, meaning faulty. So let's assume that more than 2f plus 1 abide by the algorithm, meaning that they're not faulty, they're not malicious.
Что мы также будем работать с консенсусами, с моделью частично синхронной. Что это значит?
Let's also assume that it's at least partially synchronous model, synchronous, meaning that messages can take some time to be delivered, and this time can be arbitrary, but eventually they will be delivered. So 2f plus 1
частично синхронной сети, она была представлена там в классическом.
As a model of a partially synchronous network was first proposed in some classical papers dating back to 1980s. And to this very day, we are seeing more and more algorithms emerge for use in blockchains on this basis.
То есть алгоритм решает задачу.
So how do we achieve consensus in a model like this? In a distributed network, an algorithm will consider that we have consensus as long as we meet 3 criteria. One is consistency, when all the truthful nodes accept the same value, which is correct. And by the way, we can have different definitions of correctness. We can talk of correctness in a purely cryptographic way, or we can have some external predicate that will tell us whether a value is correct or not. With a simple model, we can, for example, say that the values coming from, that member of the network will be considered correct. And completability, the most important or the most complex criterion here, it does depend on time, right? All the nodes must achieve a particular value sooner or later.
в одном раунде работал алгоритм.
Obviously, we want this criteria to be satisfied not just in one round. We want the blockchain to continue to grow.
Для каждого следующего
So for every round of the algorithm, for every next value accepted, we want all these criteria to be satisfied.
достижения византийского консенсуса является
So for the Byzantine consensus, the first possible solution is BFT. You know, this algo was first proposed in 1999.
мы обсудим, что
So in a good case, and I will later define what a good case is, it does the following. Let's assume we have a client,
команды
shown as C here, which proposes a command like
еще никакого
read and write. Back then, in 1999, there was no such thing as blockchain, which need to be performed by the nodes in a distributed network. Moreover, once they do that, their state will change in a consistent way. So the client sends a command to the leader, and a leader is one of the nodes, and all nodes know which node currently is the leader.
после того, как лидер получил сообщение, после того,
Once the leader gets this message,
он отправляет подготовленное значение, да, которое он
it will send a value or the value it received from the client to all the other nodes with a prepare message, and all the bona fide nodes, once they see it, it comes from the leader. They will respond to the prepare message from the leader with a prepare kind of ACK.
То есть 2f+1
After that, we're expecting a quorum of messages from all the nodes, like 2f plus 1.
они получили этот quorum с одинаковым значением,
So if we have this quorum,
типа commit с этим же значением,
then commit messages are dispatched. Again, we wait for a quorum.
на этом этапе они
And if we have the quorum,
на машине, это
then they will perform the command locally and they will send the response to the client. And the client is effectively waiting for the minor quorum, which is f plus 1.
команда
So once it receives this information that at least, f plus 1 bona fide nodes has accepted it, it will apparently go through. You do remember that this is a Byzantine condition, meaning that some nodes here may easily be malicious. Like none of the nodes actually knows
представлена только
whom they can trust.
хороший случай, да, что
So this
клиент отправляет сообщение
chart shows a pretty optimistic situation, something that's often called normal flow, where the leader happens to be a good node, a bona fide node, but we never know in advance if we can trust the leader.
с этим у нас возможны следующие виды византийских ошибок, да, то есть когда
So what kind of Byzantine mistakes are possible? So let's assume that the leader is Byzantine.
да, хочется включить следующий слайд. Спасибо за помощь. Да, что может произойти, если лидер византийский? Во-первых,
So indeed, what can happen if the leader is Byzantine? The leader can refuse to accept a message, or maybe it will accept messages with blocks that only contain beneficial transactions for it. So here, for example,
но не принимать.
it will accept the X message, but not A message.
Кроме того, он вообще может ничего не делать.
Moreover,
Это будет даже не византийский.
it can be lazy. It won't be even a Byzantine mistake. It will look like a regular failure.
То есть это относится к CFT. Вот. И также он может попробовать остановить работу протокола, да, то есть он может отправить
It can also try to stop the protocol down by sending one value to one node, another to the second one, and then yet another to the third one. And this way, there will never be quorum.
прогрессировать.
Consensus will stop. The chain will no longer progress.
Получается, нам вот это normal flow недостаточно.
How do we go about it? So obviously, normal flow is not good enough. We do need an additional algorithm to make sure that blockchain continues to grow. So this is what's usually called view change,
Срабатывает так.
and it activates when the timer
Есть какой-то,
is triggered. Every node
да, и
has a local timer,
по истечению него инициализируется, соответственно,
and when this timer is over, view change algo kicks in.
и схожие алгоритмы, у них во
In BFT and similar algos,
они еще пытаются принять текущее
it's not just leaders change every round, but they also try to accept when that happens the previously prepared value if it has at least gone through the small quorum.
разные блокчейны
Now, different blockchains
консенсуса под свои нужды.
develop their own consensus algorithms for their needs, and most of them,
Наследуют идею normal flow PBFT.
in fact, effectively inherit normal flow BFT idea, and they optimize view change. They can add, for example, some synchronization stages or some ways to make the process happen faster.
Соответственно, мы рассмотрели атаки, связанные с византийским поведением узлов. Но
Now, we've talked about Byzantine behavior of the nodes. But if we go back to the definition of consensus outside BFT, and it could be classic POW or POS blockchains, in proof of work, for example, there is a well-known 51% attack,
захватывают большинство вычислительных
where
мощностей, могут делать все, что угодно.
if the bad guys control 51% of the network, they can do whatever. Sybil attack is also possible. So in a federated Byzantine agreement,
Нет общего канала, а есть какая-то топология.
where there is no shared channel, but there is a, topology determines things,
Сивилы.
you can have Sybils, that's the name for malicious nodes, and they will try to change the topology of the network to isolate some other nodes.
Работу системы
And that way, they can manipulate the chain.
может привести
What can it lead to?
будет храниться разная цепочка. Да?
Well, that can lead to forks forming. That can lead to transactions being lost.
Уже произошедших транзакций.
Transactions that have already happened may then be deleted, and that can potentially result in double spend. Or the whole chain can come to a screeching halt. If consensus has been improperly designed, and I think you must have heard about Solana stoppage for a total of 100 hours, some of it due to consensus mistakes.
Да, поэтому как бы дизайн консенсусов нужно
So consensus design
при разработке протоколов.
needs to be checked. As you develop protocols, it's a good idea to analyze their security, and it makes a lot of sense to use tools for that. Now let's start with testing.
Оно необходимо, но
Naturally, consensus testing is required. If we look at some very simple tests, they can only guarantee that, a single
переходов в поведении.
like a jump is correct. When you have kind of a complex trajectories, such tools won't give you much. Other white box tools,
Уже лучше.
such as simulations or fuzzing, they are better. For sure, they can check at least, some
Не гарантируют
chain jumps.
математически корректную работу.
But mathematically speaking, they cannot guarantee that algorithms work in a correct way, though they can help you in terms of identifying mistakes. That's why they're quite effective for that. That's why they're used. Now, as regards black box testing, there are some very popular frameworks such as Jepsen that you can use to check all the attributes of consensus, and still they will not be able to cover all potential scenarios of a protocol.
Увидим, как это на практике
We are going to see a bit later
с
how it all works.
да, то есть там
In any case, we're talking here about a combinatorial explosion of states. So if you increase the number of rounds or the number of nodes
вот.
by a small margin, the total number of states you can get in will explode.
Формальной верификации, как я уже сказал,
You will remember that I'm involved in formal verification, which is effectively mathematically proving
корректно.
that our algos work in a correct way. How can you do it mathematically?
Сложные программы.
Well, you can either analyze all the states,
И все это тоже можно
or you can propose a REMA, so to speak, and then prove it.
автоматизации выразительности, да, то есть
So there is this graph of
доказательством, они
kind of
мы
Oh, right. So it's automation of expressiveness. I'm sorry, it's automation versus expressiveness. So take code, transpose it in any language, then you write your theorems in this language about this code, and then in a special environment with a proof checker, you will be developing your proof.
Генерируется автоматически с помощью SMT-решателя.
And then you can actually generate it sort of automatically using an SMT solver. So this one involves going through all the potential states. So we're effectively writing it down as a system of jumps. I'm sorry.
Проверяет в каждом состоянии свойства, описанные на языке.
So it will be checking in every state the attributes written in the language of temporal logic.
В целом,
so you will see that model checking
в прошлом году
is something that is pretty good for consensus, although in terms of expressiveness, it's nothing to write home about. So I had a presentation last year about something similar, but this time I'm talking about consensus. So as I'm saying now, model checking is actually more efficient, as proved both by theory and by practice. The theory says that consensus algos are often proffered in academic articles, and you will often have some formal description, some pseudocode that you can base your model on.
Языков для модел-чекинга оказывается вполне достаточно, чтобы поэтому...
So the expressiveness of this language seems to be enough for model checking purposes.
Есть много успешных кейсов.
So we also know from practice that there are many successful cases of consensus verification. Could be Paxos,
Tendermint, который используется в блокчейне Cosmos.
And Tendermint, which is used for Cosmos blockchain. And Chunky BFT, which has recently been verified. It is often used for the hyped-up blockchain ZK-SYBIC. And I was also involved with the formal verification of hot stuff several years ago. So what kind of language is used for model checking? In fact, there are several languages used. We are using TLE+. It has been designed for, well, in fact, model checking in distributed systems. And it's surprisingly simple. It's a mathematical language. All it has is temporal logic. I'm actually going to show what it's like. Theory of sets, I think, and first-order logic. So it's, pretty strict mathematical language. And we develop models in it. These models are not compiled. They are not expected to be executable. Instead, we have a special tool running through all the states of our model, checking if, it meets the criteria. And temporally speaking, it can go through all the branches of the chain, doing the same kind of inspection. And there are two main tools here within TLE+. One is TLC and Appalachian. They're slightly different. TLC does go through all possible states, thus ensuring full coverage, while Appalachian, working on the basis of our model, it generates a first-order formula and then feeds it to the SMT solver, which checks if it's satisfied or not. Let's illustrate it, shall we?
Как вообще моделировать консенсус на TLA+? Ну, первое, что нам нужно сделать...
So, consensus modeling on TLA+.
Вот этот общий...
So the first thing we gotta do is model the comms channel, so to speak. And we're calling this one, this set, we're calling it messages, but the name could be anything really. So in order to, when we send a message, it's added to the set, and receiving it is like checking that it exists in the set.
Ну, здесь общее определение состояния модели — это набор значений ее перемен.
So the state of the model is a set of values of its variables. What else do we need to model here? I've mentioned timers already. So when timers are triggered, a view change is initialized.
Мы должны понимать, что у нас проверяются
We need to remember here that all states need to be checked.
время. У нас
In order for them to be checked over a finite amount of time, we need to have a finite number of those.
мы будем явно
So
моделировать
there should be limitations on the model. And if we explicitly model the time,
будет очень много. Вот. И
we will end up having too many states.
мы просто должны ограничить параметры протокола.
Moreover, we need to limit the parameters of the protocol with a certain relatively small value. So we are limiting the number of nodes and rounds and other, parameters we accept. So it may possibly mean that we're analyzing just a portion of the chain.
Здесь, по сути, чисто
So you see the code here in TLE+, and this is a pure play mathematics. You see conjunction here, existence.
вот, например, upon pre-prepared — это, соответственно,
So upon pre-prepared
action,
is effectively an action, a
принять
transition, if you like,
сообщение.
when node B accepts a pre-prepared message. You will remember that such messages are sent by the leader. So we need to check that it comes from the leader, that its type is pre-prepare, that the current round is the same as the one we're expecting, as the local round value.
Во множество месседжей, сообщение типа prepare. Да, дальше
And then, once we receive it, we should send prepare to all the nodes.
узлом сообщения типа prepare, да, если он получает одно сообщение, то он ничего не
So
должен. А вот если он получает
if the leader receives like one prepare message, it doesn't do anything. But once it gets cardinality, and cardinality is like, well, the power of all messages, capacity, exceeding the quorum,
он должен
which in our case is 2f plus 1,
свое состояние
then it should change its state
и отправить новое сообщение. Как мы видим, здесь
and send a new message.
что это такое? По сути, это предикат двуместный
Effectively,
состояния на вход.
it's a predicate which can take two states.
И вот следующее состояние,
So
оно описывается вот
the
таким
next state
штрихом над переменной.
is described like this here.
Обновляем состояние,
So it's a variable with a dash.
описывается штрихом.
We update the state as we update the variables by adding dash to the formula, so to speak. So it's a very simple language, really. It's pure mathematics, isn't it?
Нам нужно смоделировать византийское,
So what else do we need to model? We need to model Byzantine behavior.
должно быть число состояний. Вот. И тут есть как бы два
And we do have a finite number of states, right? So there are two different ways we can use here. One is dynamic, where we add all potential messages from Byzantine nodes,
число состояний.
but that will result in an infinite number of states, although that's pretty realistic.
Что мы просто вначале
Now, if we do it statically,
какое-то большое число сообщений,
we'll just have a large number of messages at the beginning, assuming they all came from Byzantine nodes,
вот протокола, ну, это тоже
and see if that breaks the protocol up or not. That's actually suboptimal because in real life we'll be getting both good messages and bad messages.
соответственно, всегда будут находить кворум,
And nodes
да, и
should always be able to find quorum of good messages to progress.
мы должны где-то быть посередине, то есть мы должны моделировать
So we need to be somewhere in the middle. We want to model dynamically only those messages that can actually break the progression of the protocol. And it's up to the engineer how they actually want to model that.
нет, но вместо этого мы можем
I previously said there are no timers, but we can imagine that at any point nodes can go into a timeout or initiate view change, which is pretty realistic, right?
можем краш, может просто там кто-то вил
A crash is always possible.
в центре, да.
After all, somebody can pull the plug.
Да, то есть есть такие нюансы, связанные с инструментами, что по умолчанию TLC, например, всегда предполагает наихудший сценарий.
So by default in TLC, we assume the worst is possible, like all the nodes can crash at the same time. We can use temporal logic here and assume that, okay, not all the nodes will crash at the same time. Now let's look at specific cases, shall we?
Протокол BFT консенсусов. И первый алгоритм — это IBFT.
So the first algo was IBFT.
Еще перед этим, наверное, хочется сказать, что в принципе...
Before I do that, however, I should mention that all these tasks of testing and verification of protocols, they've not been
универсального инструмента.
satisfactorily resolved, so to speak. There is no silver bullet, that's what I'm saying. We cannot really guarantee the protocol is entirely correct in a very convincing way, so to speak. So let's go back to IBFT. What kind of protocol is that? Well, it's been inspired by BFT.
Для блокчейна Quorum.
So it was adapted for permission to blockchain. So it was not public, obviously. Now, it dates back to 2017. It was proposed as, Ethereum Improvement Proposal 650, and the idea was that it would have a dynamic set of nodes, that's validator nodes, and the idea was that, nodes would be sending their block proposals to the system, like there is no external client. Well, in fact, the normal flow here is very similar to BFT. The only difference is here. Round change algo here is slightly different. So you see that, they've somewhat optimized communications, but this is it really. So when it was first proposed, it did not really provide proper consistency or completability, but then additional studies were published.
Доказательствами корректности. Ну и пришли к какой-то вот последней версии, которая используется.
So the latest version, which is currently used in Quorum,
соответственно, написали модель на TLA+, и проверили для нее...
Inspired us to develop our model TLA+, and we decided to check its safety and liveness.
Согласованность и корректность принимаемых значений. А liveness — это, соответственно, темпоральный...
You will remember what liveness is. Liveness is a temporal attribute that, over time something good is going to happen.
Примет какое-то значение. Вот так они...
So eventually the node will accept a particular value.
Здесь написано, что там для любых...
So this one effectively says that for any two distant nodes, if they accept a value, it will be the same value across the two. So the diamond here is eventually temporal operand. So sooner or later, eventually, if you like, it will accept will make a decision and will accept a value which is the same between the two. You can read more about the technical details if you follow the QR codes. You will find the article there and the model itself.
Внимание на, соответственно, что такое комбинаторный взрыв, как это выглядит на практике.
Here I want to explain what combinatorial explosion is. So let's assume we just have 2 rounds, so we do not model Byzantine behavior. It takes the model just 1 minute to check. We have 5 rounds, and we add like 1 Byzantine node.
У нас уже неделями измеряется срок проверки.
The checking time can be like 18 days.
Результат получен, да? Ну, другое дело, что если мы увеличим еще параметры протокола.
Now imagine that you expand the parameters of the protocol even further. You probably won't live to see the end of the checking process. This is what I call combinatorial explosion.
Не самый сложный BFT протокол.
Now, a BFT is not the most complicated protocol. It's similar to BFT. Its formal description is easy to understand. It doesn't have any complex features in terms of synchronization, for example. Now let's look at a more interesting protocol, which is SmartBFT. SmartBFT is used in Hyperledger Fabric. Hyperledger Fabric until version 3.0 used CFT Raft consensus.
Соответственно, повысить отказоустойчивость.
And I think they wanted to increase their fault tolerance and to be better protected against Byzantine mistakes.
Видимо, подходящий...
Apparently, they were not able to find the right kind of consensus.
ordering service.
So consensus is actually part of their ordering service, the service they use to order their transactions.
Гошные интерфейсы были у, соответственно, реализации консенсуса. Ну и вот написали
So they ended up producing their own SmartBFT library.
В чем ее особенность? Ну, то есть там тоже какая-то оптимизация коммуникационной сложности относительно PBFT.
It did involve some optimization of communication complexity compared to PBFT. It's based on PBFT and PBFT Smart.
Как мне кажется, да?
It's a practical application. Obviously, they did not have, academic ambitions. They did not provide a formal academic description, which makes model reconstruction a bit more difficult. Like you need to analyze the code, do away with additional variables in order to reproduce their model.
Узлов, там есть модель чекпоинтов.
It also provides for node synchronization. They also use checkpoints and for system reconfiguration as well.
Да, то есть normal flow SmartBFT такой же, как в PBFT.
So the normal flow for SmartBFT is the same as it is for PBFT. You've already seen me model it for TLA or in TLA+. And view change comes from BFT Smart. And it's optimized for HLF goals. So how does it change the round? Nodes trigger their local timers, they go into timeout, they signal it with view change. Then every truthful node waits until the small quorum of view change messages and sends view data message to the leader with its current prepared value.
Лидер дальше все это обрабатывает.
The leader then processes it all
сообщение типа new view
and sends new view message with the prepared value they need to accept in the next round, and then they all proceed to the next round trying to adopt the prepared value if it's valid. So you see here the TLA plus code.
Действие обработки лидером
What's happening here?
сообщений типа view data получено.
You can see here the leader processing view data requests from other nodes. What can happen here?
Фаза view change, ну, это вспомогательная переменная фаза.
So obviously we are going through the view change phase now, and there is a check if the leader is the leader. In this block,
Закоммитить сразу
it can accept and commit a checkpoint of another node
обгоняет его лог.
if such a checkpoint is ahead of its block by exactly one.
Одно значение больше уже принял, вот, и, ну, конечно же, это там значение как-то еще проверяется, ну, проверяется
Well, naturally goes through some checks, including cryptography checks.
Вот, кроме того, затем, соответственно, проверяются присланные подготовленные значения.
Afterwards,
Называются in-flight.
the submitted, they call them in-flight values, are checked. They check for quorum.
И отправляется, соответственно, сообщение типа new view. Вот.
And then the new view message is sent. In the new view phase, if nodes see that they are behind the log by more than 2 cells, they go for an additional synchronization stage. So this model is much more complex because it goes through so many more states. I'm just showing a portion of the model. I'm just trying to show that, we've modeled it all.
Она уже гораздо сложнее, но ее получилось проверить для...
So we have been able to check it for 4 nodes, with 1 being Byzantine. So there are 3 log cells and 3 rounds in TLC.
Также был
So by going through all possible states, it took us like 20 days. And then we ran like 1,000 simulations on Appalachian for the same setup and 5 rounds.
Было проведено там порядка 1000 симуляций, уже там для 5 раундов, и ошибок в модели не было выявлено. Вот,
And they did not discover any mistakes in the model. In terms of liveness, the time went through the roof, really. So liveness, obviously, is a measure of whether the blockchain is going to progress or not. And the reason for that is that checking temporal properties is requires much more resources. You're checking through all the invariants.
Вот. Ну, и также здесь на самом деле можно проверить, но для этого нужно менять модель синхронизации тайм-аутов, да, то есть делать какие-то...
We can actually, check it, but that would require some simplification.
И ценность в этом будет небольшая.
Meaning that, the academic value of that will be minimal. That's why we decided to go back to formal proofs. Formal proofs for a consensus do have some benefits. A, we won't be limited in terms of the number of parameters, like 4 nodes and 5 rounds. Doesn't feel like a lot, right? Moreover, you have a higher level specification there. And you won't have this combinatorial explosion. So we have a theorem stating that for any number of nodes, we posit that we will arrive at alignment. In practice, however, it's still pretty resource intensive. Even if you're using COG and similar tools, it can easily take upward of 6 months. And this is also proved by, seeing the history of commits in the project. So even if there's no Byzantine behavior there, though, some people tried doing this verification in COG, and it required 40,000 lines of code in more than 6 months, while for BFT, it required 70,000 lines of code. And I think that in this project in particular, a portion was related to code generation. So they generate code out of this model, and they checked it for consistency with BFT semantics. Lean 4, a tool, is getting more popular now, and it is sporting now frameworks for verification of distributed systems. And LLMs are now being taught to use Lean 4 to prove or disprove theorems. They're mostly using it for classic mathematics. So far, I have not heard of any outstanding results coming from that.
Ну, а для реальных систем, как мне кажется, все еще хуже.
And I believe that for real systems, it's even worse. So this is more like a potential future at this stage. To summarize, model checking appears to be the most efficient method. On the one hand, it's still a rigorous, formal, mathematical guarantee that the system will work in a correct fashion. On the other hand, it does not require a lifetime. So the two examples I've showed today hopefully serve to prove the point. I actually have more examples. You can, click the links in my presentation. I will upload it soon.
Здесь мы упираемся в ограниченность вычислительных ресурсов, то есть в комбинаторный взрыв, что у нас просто модель может бесконечно.
Remember what I said previously about combinatorial explosion? This compute constraint will be probably the most important constraint. But if you want to run your formal verification process faster,
если там есть какая-то документация, писать псевдокод, чтобы можно было понимать...
It should make a lot of sense for you to produce your pseudocode so that, you can see what you can optimize in your model, what you can shed for verification purposes and whatnot. I think this is it for my presentation. And this is my Telegram if you are interested. This is my email. Like, if you want us to do audit, you should realize now that we're not just auditing smart contracts, but we can audit your consensus for you. In fact, we can do lots of things around blockchains. Thank you, Kirill. Do we have any questions? If we do, please use the mics. We've got 2 mics.
Thank
you very much for this presentation. Can you kindly tell us why or like how are you using it all? Was that an academic study or are you actually making money doing that? That was a research with the objective of then delivering potentially an interesting presentation. But I think we're open to commercial proposals for sure.
Сетевые протоколы, ну, то есть вот есть вот эти ноды, да, они между собой взаимодействуют.
Okay, these nodes interact with each other.
Они
Now, there were vulnerabilities in blockchains such as Solana. They were not related so much to the consensus,
например, в Solana.
but that was the case of UDP and Quick in Solana, for example, and there were some vulns in Near related to transaction parsing.
Верификация.
Do you do verifications like this?
Если бы вы делали бы такие исследования,
Yes, we do that.
как?
Like, imagine you were running a research like this. How would you do that?
Как я сказал, и для распределенных систем, и для
Like I said, both for distributed systems
другого кода
and other algos,
серебряной пули, который все решает. То есть надо,
there is no silver bullet.
ну, чтобы построить
You start by looking what the code is written in.
для разных там исходных языков разные инструменты.
You gotta see the source code
Нужно смотреть,
to come up with the right model, because there are different tools and different frameworks used out there.
то есть,
I would probably start with the deductive method, so to speak. I would first, transpose the code of the software to Coq and start with a theorem that nothing bad is going to happen and see if it can be proved. A question about model checking.
Вы ограничены.
Doesn't your example show that you're limited in terms of the number of nodes you can simulate? That's true.
Не знаю, там 500
Doesn't that mean
это пиковые значения как раз для
that, with peak numbers of nodes like 500,000, which isn't the peak value, so to speak, for real blockchains, you will be experiencing problems you have not seen here? That's a good question. I do understand it's a relatively weak assumption.
все-таки измеряется число.
In private blockchains, however, you usually have dozens of nodes, not hundreds.
Достаточно. То есть так,
ну, в
такая-
Tendermint, например,
This assumption, however, in most cases will hold. Tendermint is not private.
важный момент, что да, здесь
I
есть
should have mentioned something else here.
вот, например,
I'm not stating this is like a state-of-the-art solution, right? They promised to expedite TLC by 1,000 times. So if checking happens much faster, obviously you should be able to play with many more parameters and increase the number of nodes. So I'm not saying it's ideal, but at least this is something, right? Thank you.
Спасибо за доклад. На самом деле мой
Thank you for your presentation. My question has already been asked.
то есть
I had the same concern, really.
с одним
Your experiment ran on 4 nodes, with one of them being Byzantine.
не дает нам права говорить, что
In my opinion, it doesn't really empower us to claim that this protocol will be reliable on a dramatically different number of nodes. Did I get it right?
ну, то есть это уже хорошие гарантии на самом деле. Вот.
In a way, it's already a pretty good guarantee.
В других инструментах доказать.
You can actually try using other tools and proving some other theorems.
Соответственно, если увеличим число нов, там ничего.
извините, да, я как бы не принижаю вашу работу.
Да, я
I'm sorry, please don't get me wrong. I'm not trying to pour cold water on you in your study.
в принципе,
I see that.
работает, то там тоже нигде
I'm just saying that in other studies,
не ограничено,
you can find
наверное, 7 узлами, да.
nobody has been using more than 7 nodes.
Про BFT like consensus
Now, when we are talking about BFT-like consensus,
валидаторов,
even if we are looking at a broad range of validators,
множество валидаторов, которые уже, в зависимости от блокчейн-платформы, там по-разному могут подходить.
depending on the blockchain platform, you can,
Валидируют объект
within a particular epoch, decide on the number of validators you need one way or another. Now, when we're talking about a blockchain for like 100,000 validators,
того или иного блока, не все 500 нод подписывают, они
it's not like, all the nodes will be validating. Most of them will be sort of accepting the decision.
принимают результат голосования
they will be accepting the result of the vote of a pretty limited subset of nodes. So if you have like 500 nodes and all of them are validators, the communication complexity will go through the roof and consensus will be hard to find. So the big question here is whether like 4 nodes is enough or not. I think it's a good question.
Который состоит из потенциальных там 500, 1100 нод. Потому что на самом деле-то они не все занимаются в BFT-like.
And I believe that BFT-like consensus does not really happen in really huge systems. In Solana, you also have leaders, right?
В консенсусах.
So it is an additional condition to remember about in consensus.
Сделал утверждение, все остальные подтверждают это утверждение.
So in a proof-based consensus, you need every node to perform the calculation and arrive at the same proof. But here we're talking about consensus in its kind of classic understanding.
Доказал до одного узла, для двух узлов.
What about like mathematical induction here? Like you've proved it for 2 nodes and therefore it will hold for 3 and so on. That's a good question. We got to think.